So here we are on page 202, 6.3 uniform circular motion. Now the textbook, they like to cover uniform circular motion in about 2 little segments here under applications of Newton's laws. It's a little bit more challenging than that, I found, over the years. So just quickly, we're just going to skip through a few things here under 6.3. First of all, I'd like you to look quickly at the picture on page 203. Nothing to do with physics, but I'd like you to look at figure 613 and 614 and tell me if you see any problems.
Not 600.
One of those 30 seconds. One of those 60 seconds.
Exactly. Very good eye there, Zach. The actual stopwatch actually goes all the way around 30 seconds, but the picture of the stopwatch goes all the way around in 60 seconds. So 2 things come to mind. First of all, why do they make stopwatches that take 30 seconds to go all the way around instead of 60?
Why not?
I guess, why not? But there must be a reason for it. So? Now, this is not a digital stopwatch.
It's more precise.
It's more precise, exactly. It's more precise because now the tick marks are, in fact, like the 1 second would be twice as far as it would be if it was 60 seconds all the way around, right? So you can actually read it a bit better. It's more precise. Again, that's an analog stopwatch. You're like going back to the 60s and the 70s there. Nobody in their right mind would probably use an analog one anymore. But once again, my second comment here is, once again, the textbook people making a mistake. The artwork people not collaborating with the math people and making mistakes there. So you can read through that. It's not really that important, kind of. Okay. They talk about centripetal force, centripetal acceleration on page 204, blah, blah, blah. Eventually on page 205, they come up with the formula A equals v squared over r, which we already know, right? We know that the velocity is 2 pi r over t, and acceleration is v squared over r. And I think, if I'm not mistaken, on the very next page, they also come up with A equals 4 pi squared r over t squared, right?
Yes.
Okay, so those are the 3 that we've been using. Now, they also show this one. Now, how do they get A equals 4 pi squared r f squared? Well, you may remember from a further discussion or previous discussion that 1 over the period is equal to the frequency, right? Which means that if you square both sides, 1 over t squared is equal to f squared. So if you've got over t squared here, that's the same thing as just having f squared. So you might actually want to jot that formula down. That one actually comes in handy when you're given the frequency. Rather than having to convert it to the period, you just sort of build it into the formula. 4 pi squared r f squared. And that's another good reason why we don't use the magic triangles to solve equations anymore, because it's kind of challenging.
Metric worked really good though in grade 11.
Yeah, for a while. Now, I would recommend that you have a look at some questions on page 206, numbers 1 to 6. Mary, I drives me to listen. Stop listening. Okay, so page 206, numbers 1 to 6 would be some good ones to have a look at. And now you'll notice that if you go to page 207, now they talk about centripetal force. They basically take all of those formulas that we just had for A and stick an M in front of them to get force. So now they show them in a little box there. They got mv squared over r, which we already know. They got m 4 pi squared r over t squared, which we've already seen. Plus, if you stick an m in front of this one, well, then you get m 4 pi squared rf squared. That's a mouthful. Okay, that's all on page 207. So again, those are just some different tools that you can use. It's really no different than we've already seen. It's just a rework of that t squared. Okay, now I gave you a sheet today. It's got example, is it 7 and 8? Is that right?
Yeah.
Okay, so let's just have a look at numbers 7 and 8, and I'm going to look at bank curves tomorrow. Okay? No, here's number 7 right here. Now, I took the liberty of typing it out for you so you don't have to type it out. And also so that you've got it, because, you know, when you're taking physics next year and you want to look back at your notes, because no one's going to throw their notes away at the end of this year, right?
Wait, how did I take this next year?
Yeah, I was assuming everyone's going on yours, exactly.
Yeah, but like, none of us.
Yeah, I know. What are you going to do? No. Wow.
You gotta take computer science or something.
Good.
Math.
All right. So once again, We're on page 208. Here we have a 20-gram flea sitting at a distance of 5 centimeters from the center of a rotating LP record. Anybody want to take a guess what LP stands for? Is that what it says that in the book? It does. Anybody know what an LP record is? Okay, first of all, do we know what a record is?
Yes.
Okay, we do know what a record is. It's a vinyl record, right? From the good old days. LP stands for long playing because you could put, wait for it, 5 songs on a side.
What?
That's a long time. 5 songs. Sometimes 6.
And you flip it, and there's 5.
There's another 5 or 6 on the other side. You see, in the really, really old days, they only had 1 song per side. So these new inventions, long playing.
They used to have the books that you could read and they could read along. Right?
Yeah, I never had those. So that's what they mean by that. Now it says the record rotates at 77 RPM. Now I don't remember. I know the big ones there, you know, the kind that Stashko's dad probably has at home. Those are 33 1/3 RPMs. The big ones, the ones with 5 on the side. These LPs here, I'm not sure what they're talking about. I know my grandparents had, I think they were 78 RPM. I don't know where they got the 77, but they were really, really, really old records. And then the single ones, they are the little 45. You know those kind? You ever seen those?
Yeah.
Just a single song. Okay, so anyways, what centripetal force must be provided by friction to cause the flea to maintain its UCM? Now, I'm just going to sort of ignore the book because they always make things confusing. Now, did something twig? Did you realize that that's 20 grams and you're going to have to convert it to kilograms? Did that clue in on you? And did you realize this is 5 centimeters? You're going to have to convert that to meters, okay? So what do we know here? Let's just write down what we know. We got a mass of, now, 0.2 grams divided by 1,000, that's going to be 0.0002 kilos. My radius is 0.05 meters. 77 RPM, revolutions per minute. Is that a frequency?
Yeah.
It's a type of frequency, but frequency has to be in revolutions per. So what do I have to do?
Divided by 60.
Exactly. So my frequency is 77 divided by 60. Now I'm going to have to get a calculator.
That's very slow.
77 divided by 60, so it goes around 1.28 times per second. Did we talk about the unit for frequency? Hertz, right. Hz, hertz. And we are looking for centripetal force. We're looking for Fc. So what formula do we have that has has FMR, which one? Isn't it one that the one we just came up with? I think it is, right? So Fc is equal to M4 pi squared. Is it R squared? No. R F squared. It is kind of wild, isn't it? Yeah. Okay, so now I guess it's just plug and play here. So that's going to be 0.0002 times 4 times pi squared times the radius of 0.05 times 1.28, and don't forget to square that. Okay, so 0.0002 times 4 times pi squared times 0.05 times 1.28 squared equals 0.0006.
I think it's 0.
What'd you get?
647, I guess. Maybe we should convert that to scientific notation.
Nah.
1, 2, 3, 4 times 10 to the minus 4, and that's newtons. Now, does that make sense that it would be such a small little number?
Yeah.
It's just a little fleet, right? Where does that force come from? Like what causes it? It's the flea's sitting on the outside of the record. Let me just draw a little picture here. Here's the sort of the post in the middle.
Because there's G's acting on the
Right, and there's the record, and here's our little flea out here. But what's producing the force to make him go into the center? Right.
The hydrogen, helium is the sun.
Good guess. Yeah, good guess. Do you remember when we talked about going around a curve in your car and what actually makes the car go sideways? Friction. Friction. So it's actually the friction between the vinyl and the flea's feet, I guess, that actually are doing that. Now, would there be enough friction to produce 6.47 times 10 to the minus 4 newtons? Like records are kind of rough, aren't they? They got those grooves in them. I think that's the answer. I think that's the answer. Okay, are we good with that one, do you think?
One formula.
Yeah. Let's have a look at example 8. Here we have a chestnut. Could be any other form of walnut. I don't know, walnut. Any other tree nut would be fine. Quinn, put the phone away, please. Acorn, possibly, yeah.
Isn't that like 0.25 kilograms?
Yeah, that's hefty, isn't it?
No. Isn't that half a pound?
Well, actually, if you read the book carefully, Zach, it says a 25 kilogram chestnut. You're right, it would be about a half a pound. A 25 kilogram chestnut with a hole drilled through its center is hanging from a long massless shoelace. What does that mean, a massless shoelace?
25 kilogram chestnut.
In the book, it says 25. Up there, it says 250. I'll explain in a second. Okay? Well, I want to know what does the massless shoelace mean? What does that mean? It means that we don't care about the massless shoelace. Does the shoelace actually have mass? Of course it does. But we're just ignoring it for its purpose. A child spins the chestnut in a vertical circle at a speed of 4 meters per second. If the shoelace is 0.8 meters long, determine the tension in the shoelace at the top and the bottom of the circle. Now, as soon as you go down to the given, then they write given m equals 0.25. So the book actually says 25 grams, but then the given is 0.25 kilograms, which is obviously wrong. And then they actually go and they use that 0.25 throughout the entire solution. So I would agree with Zach in that a 250 gram chestnut seems awfully large. It's some sort of mutant chestnut, perhaps. But it seems easier to change the question than it is to change the whole solution. So, good with that? All right. So we've got m.25. The speed is 4. The radius is 0.8. Okay, and we've got it traveling in a circle. We've got tension at the top. We've got tension at the bottom. We'll call this T up, T bottom. Where's the tension greatest? At the bottom, right? Okay. Are we going to need the weight force here?
Yes.
Absolutely. I'm kind of at a bit of a loss here, so I'm going to start finding the weight force. How does that sound?
Yeah.
I'll start with that. FW is equal to mg. It is negative, isn't it? Yeah. Yeah, well, we're operating in pencil here, so we should be okay. .25 times 9.8, 2.45 minus 2. Whoops. Minus 2.45 newtons. Okay, now the centripetal force is Fc is equal to mv squared over r, right? So that's going to be 0.25. My velocity is 4 squared, and my radius is 0.8. 0.25 times 4 squared divided by 0.8. Exactly 5. Exactly 5 newtons. Okay, so let's stop and think about this for a second. So I need 5 newtons of centripetal force to maintain circular motion. I got a weight force of minus 2.45. Now at the top, what makes up the centripetal force? What 2 things are contributing to the centripetal force? The tension in the string and gravity. And at the top, they're sort of working together, aren't they? And at the bottom there, they're opposite, exactly. Okay. So at the top, my centripetal force is made up of the tension, right? At the top, and I'll just draw a little picture here, they're both down. In fact, the centripetal force is down, isn't it? The overall net force is down. I'm just going to write tension plus weight force, and then I'm going to throw my signs in properly. So, yeah, how should we show FT? Okay, sure. FT. I think I called it FS, string force, I think, before, didn't I? Okay. Okay, I'm good with that. So the centripetal force at the top is going to be minus 5. Now, why is it minus? Because it's down. Exactly. Is the tension force also down? I think so. Well, I sure hope this works. Now, but I don't know what the tension force is, so I'm just going to write FT. Now, my weight force is negative 2.45. So when it goes to the other side, it's going to become positive, and I'm going to have minus 5 plus 2.45. And why am I getting the calculator? Because I know the answer. You should get FT is equal to, no, this is at the top, minus 2.55 newtons. The tension is down. What does Cody say? So important. Okay, tell Cody that you have to listen. Stop texting me. So does that make sense? Tension force minus 2.55? It's less, right? We made it less than the centripetal force. Okay, now what's going on at the top or at the bottom? It's exactly the same scenario except at the bottom. Now, do I think I have room there on the side to do it? It'd be nice to squeeze it in there. Or should I go underneath? I'll go underneath. At the bottom, I've got my FT and my FW. At the bottom, I've got my T is up, but my weight force is down. But same scenario. FC is equal to FT plus FW. The centripetal force now is which way? It's now up, isn't it? Right? The centripetal force is up because it's trying to pull it up. So now instead of minus 5, it's actually 5. My tension is what I'm solving for. My weight force is always down, so it's going to be minus 2.55. Oh yeah, 4.5, thanks. So now when it goes to the other side, it becomes positive, and I get a tension force of 7.45 newtons, which makes sense because it's got to be. So if you're swinging a string in a circle, a vertical circle, when is it most likely to break? At the bottom. At the bottom. Right? At the bottom. Which means that it would actually likely go? Well, if you're swinging it this way, right? You don't. Forward or backward, I guess, right?
You didn't put the negative 5 to the top.
I did, right there.
Would that really be wrong?
Oh, right there?
Would that wrong?
Well, yeah, because then you'd end up with this, wouldn't you? Right, but like, are these any different? The only difference is that sign on that one.
Okay.
So yeah, that's significant, isn't it? Yeah. Okay, if you flip the page or just at the bottom of the page there, they've solved it. They got similar, almost the same thing. Bottom of page 209, it says there are 2 things of note in this solution. First, note the direction of the tension of the top and bottom circle. We did that. At the top of the circle, the tension is downward toward the center of the circle. At the bottom of the circle, the tension is upward, also toward the center of the circle. In each case, the chestnut is being pulled towards the center. All right, awesome. Flip the page over. Second, the magnitudes of the tension at the top and the bottom of the circle are not the same. At the top of the circle, gravity applies a downward force toward the center of the circle, providing part of the centripetal force. As a result, the rope can apply a smaller force than would otherwise be needed to keep the chestnut moving in a circle. At the bottom, on the other hand, the shoelace not only applies a force upward to provide the centripetal force, but it must also apply an upward force to balance gravity. So tension in the shoelace is greater at the bottom of the circle than the top. There you go. We've already talked about that. Okay, so if you happen to be one of those ones that wants to read ahead, you can look at bank curves. Now, they actually spend a little over a page on bank curves. They need to spend more time on that, and we will. I've cooked up some examples for you.
Well, this is kind of like probably a week.
No, it's not. It's not quite that far. Okay. So, where are we at here now? So you can now do those questions on page 206 that I pointed out. 1 to 6, I think. As well as, there's a few questions on page 226. Number 15 to 25. There's a few textbook questions there. I know I have solutions to those somewhere. One of the things that I know is on the course outline is, or the curriculum I mean, is converting G's to meters per second squared. Quinn, I think you were asking about this the other day, right? There are occasionally, they provide you the acceleration in G's, right? So 1 G is equal to 9.8 meters per second squared. 2 G's would be 19.6, and so on. Now, do you remember in the car loop-de-loop where the guy drove the car? Oh, I didn't link that to it in school. Did you do that? Do you remember how many G's he was pulling? Was it 5? 5 or 6, something like that? Yeah. Yeah, I think that's probably pretty much at the outer boundaries of human capabilities. The fighter pilots, they have a suit when they're pulling G's like that. Their legs and their suit will actually compress, and it forces the blood that's in their legs, forces it back up to their head so they don't black out. That's how they work. That's kind of it. Okay, I'll give you the rest of the period. We'll work on bank curves tomorrow.